Hello, I was doing a technical rescue classroom discussion the other day, and there were a lot of questions that came up about forces in highlines. So I thought that rather than sending an email out with a ton of equations in it, I found this program today, Autodesk Force Effect, and I'd show you what some examples can do. So before we get into highlines, this is going to be just a regular anchor that we usually do on just about any tech rescue setup. I made it a 10-foot span here and a 6-foot extension. So you can see those numbers here. This is 6 feet. This is 10 feet. This is kind of the limit of what I would like to do usually. We always say 90-degree angle here is the most you can do safely. This one, 39.8, 39.8. So this adds up to just a hair under 80 degrees. So this would meet our safety requirement of less than 90 degrees at the base here, but just barely. So this would be considered an acceptable anchor, but I wouldn't want to do any less than an extension on this. So we can fix these two ends. We can put our load here. We typically assume a rescue load of 600 pounds. And that shows us our forces in the anchor legs here. So this is 390 pounds in each leg because this is a symmetric anchor. If we move this over to one side or the other, we can see that the forces change. So whichever anchor we're closer to, that leg of this anchor is going to have more load in it, 470 pounds versus 276 pounds. So this is just the basics of how this thing works, how forces work with these angles. And a lot of people are accustomed to dealing with this in anchors. Well, it's really the same thing for highlines. So here's a highline example. This one has 10 feet of sag in the middle here and a 100-foot span. So we divide 10 by 100. That gives us a 10% sag if we do it in percentage, which is usually how it's discussed. So we have our two anchors here. This is our track line, or our track lines, probably plural there. Our 600-pound load, and it doubles it. So the load on the anchors is 1,529 pounds. Something that you'll see if you do the math here is that the highest load as you traverse this highline system, the highest load in the system is going to be at the center. So if we take this and we drag it over towards one edge, we can see that the load goes down a bit, which is good. So our highest stress point is going to be in the middle, which means if you have an adjustable track line, or if you have adjustable track lines and you have clearance, it might be good to let out a little more rope when you get into the middle. That will give you a little more sag and reduce your forces. So here it is here with 16% sag, 100 feet still, 16.4% or 16.4 feet, so that's 16.4% sag. And our numbers have gone down quite a bit, down to 958 pounds from the 1540, something like that. I had a short memory today, 1529. So here, this is exactly 15% sag. I set this one up just to show you what the numbers would be. So this is 15 feet, 100-foot span, and it gets you down around 1,000 pounds, which is a little more reasonable. So generally, the more sag you can have in the middle here, the better. This is an example of what not to do. This is 5% sag. I don't know if I can click on this line with that force there. I'll go ahead and delete it. So here's our system with only 5 feet of sag here in the middle on our 100-foot span. So 5% sag, and when we put our rescue package load out there of 600 pounds, these vectors don't even fit on the screen. 3,000 pounds of load. So don't do this. Don't get any less than 10%. It would be better to have more than 10% sag. So, I'm still drawing forces. We don't really want to do that just yet. So, short version, keep it to 10% sag or more, and the more the better when it comes to that. Here's another example people asked about last night, and this is when it's on an incline. So one end of our high line is higher than the other. This is pretty common in the field, but the math is much more difficult, so it's not an example typically covered in a classroom scenario. but here it is. So a couple of things you can see about this. The load is still going to be the highest at the center span. We are going to have more load in this case on our top anchor than on our bottom anchor. Now what that really comes from, it's because we're doing a static analysis here instead of a dynamic one. This force has to get held up the hill, so otherwise it would accelerate to the right here. So really what we're showing is this load is the load in our track lines plus the load in our tag line that would also be there. But anyway, this is a neat little tool. If you want to go to this website, forceeffect.autodesk.com, it's free. You can sign up if you want, like I did here. But you can draw your systems in and move them around and see what the forces do. And it's a pretty handy way to just get a feel for what's going to happen with your rope systems. So there you go. If you have any questions, let me know in the comments here, or you can send me an email. Have a good one, and stay safe.